Hi all, this is Iron Geek. Unfortunately, the microphone was plugged in, but only into the camera and not actually into the mixing board. So I'm afraid this is, well, all the audio we got for the first 14 minutes or so. So skip forward 14 minutes if you don't want to see the slides, and the presentation should continue from there with sound. Thank you.
such things as if you're asking to log in as root or admin, maybe that's a hard question. Maybe we should ask for additional work computations for you just because you're asking for privileged accounts. Which kind of brings up this idea that we're trying to increase the trust or confidence with more factors. If you bring in tokens and certs, maybe we can bring a confidence level to that. So on the server performance,
the good news is that it's all pretty much good news. I'll bring up that the nonce generation may be a bottleneck because it's something that we have to do every time on all clients, irregardless of everything. And I mentioned it because we don't want to skimp on that by trying to improve performance by going down on the randomization of the nonce. The good news is the proof of work verification is fairly quick. Once you get it back, it's easy to compute the answer and verify it. It also gives us an opportunity to check the proof of work before considering other authentication factors on the back end. So if you tried to log in and you didn't provide proof of work, maybe I won't bother going to an LDAP or an AD or a database backend to verify any other credentials, and maybe locking out accounts if you're not even going to bother to fill out the proof of work. So on that, the proof of work difficulty according to load, I bring that up again because it's sometimes these servers have, especially busy ones, have problems with flash mobs where lots of valid users come in all at once because you're in the news or something. And this gives you the opportunity to push back a lot of valid clients and let them trickle in as they compute all these works. And as your load increases, you may push them back farther to sort of protect yourself from that. So on the client side, this technique is essentially slowing down the login speed. And there's a little bit of a Goldilocks area for this. If you go too slow and you give them too much to work, they're going to end up complaining about slow logins and servers not responding. On the other hand, if you go too fast, it's actually not enough of a work to be a deterrent for people who are trying to abuse your system. So the average compute times of a lot of these are decent. They're okay. The problem is mainly with the outliers, that the average times work out really well, but the confidence interval to come up with an answer, no one really knows given the particular nonce. And since you're searching for a partial collision, no one's really too sure how far you have to search. It was either you got it right away or it could be a long time, depending on where you're at. And since this is a JavaScript implementation, the JavaScript engine can make quite a big difference, even though you wouldn't think it would be a big deal. You'll see in the next slide that it's quite interesting. So sorry for the busy slide. You won't be tested on a lot of this stuff. So here's some proxy execution times of some well-known hardware, just to give you an idea of what we're talking about. On the left, you have execution time in milliseconds, and along the bottom, what we did was we took the average number of iterations for a search per number of 0 pads, and then ran it across a bunch of different hardware, a lot of the same hardware with multiple browsers, to try to illustrate not the differences between them, but mainly a couple things. One thing is that until you get to about 10 number of 0 bits in a partial collision search, it really isn't a lot of work. It just goes really fast, and it's on par with you downloading the actual script and trying to execute it. Around 10, 11, the numbers start to climb, and then after that, things just keep on going. If we kept this graph going, you would end up with a the expected hockey stick graph. that would go on. So the only other details I want to point out, I went to 19 because of a couple practical problems, such as like an iPhone 4 on SHA and MD5 starts to exceed 50 seconds execution time trying to search. Because of the outlier problem, and outliers sometimes being 2, 3, 4 times above the average, you could be in a situation at 19 bits with an iPhone, somebody having to execute, it could be taking minutes, which obviously at this point they think something's broken and then they try to reload. The other thing of note is the differences in the JavaScript engine. You can kind of see it, it's all mixed up, but a MacBook Air running Safari is all the way at the very bottom, and at 19 bits will come in at 5 seconds, but the exact same MacBook Air running Opera is at 25 and 30. So even the differences between JavaScript engines will start to diverge enough that the practicality at higher bits, the JavaScript engine is very important, the CPU, and the differences make it, impractical for a large audience. So along that, the takeaways from that is we're trying to start at 11 bits because that's a good place to start. The average among all the platforms is 50 milliseconds. And we're ending at 18 because at this point, phones start to be problematic. And as always, these are averages. You could have gotten it right away. It could be faster. It could be horribly slower. Philippe?
Okay, so we're going to talk about attacks. There's multiple way to attack that kind of system. You can pre-compute all the possible proof of work, but with 128-bit nonce, it's not going to be very practical in terms of storage. Maybe if you're NSA, you can do it, but for everybody else, that's not an option. You can run the JavaScript that we send you on the CPU. That's not very fast. So as an attack, it's not very practical. Also, that means that your attacking tool needs to have a JavaScript engine. Or you can write specific attack code, which is CPU or GPU based. So could we get an edge with a GPU? Yes. Yes, you can get an edge with a GPU. If you look at 12 bits, 12 0-bit proof of work, you can actually compute all of that in parallel with the latest graphic card. You've got 5600 cores, so you just affect one core for each number. It goes fast, but we can also cycle what algorithm we are asking you. So it's getting a bit more complicated. And if we use not only a hash, but a password stretching algorithm there, it may not be possible to compute that in GPU. The big thing is that at the end of the day, whether you find a shortcut or not, there's no free lunch. You're going to have to spend the cycle to compute that proof of work. The only way for you to get an edge would be to find a solution to that proof of work that is not an exhaustive search. So you'll have to do some pretty heavy crypto work and find shortcuts there. That may not be as good because we can cycle the hash algorithm on the server really, really fast. We just change a variable, said, okay, no, you're not working with SHA-1, you're going to work with SHA-512. And in 2 years, we're going to change that to SHA-3, or we're going to use something else. We also explored what we call meta-hash. We're going to ask you to compute not one proof of work, but multiple small proofs that you're going to chain together. Each of these proofs can use a different algorithm, and the chaining is random. So if you want to attack that, you have to be able to do an analysis of the work we're asking you and find shortcut doing that. At the end of the day, escalation is going to catch up with you. If you can make a good guess within the first 10 guess, you're good. If you need to do 1,000 guess on a password, you're going to have to do that very, very slowly, or we will escalate the work on you and we will kill your compute power. So that's going to cost you there. We consider it that more a deterrent than an authentication factor, but we would like to see that as a generalized system. The computational cost of attack has to be greater than the computational cost of defense. Our goal is to make sure that if you're using password stretching, spending 20 million cycles to defend your password, the client has to spend 40 million, 60 million cycles to do a submission. You can look at that as a tax on login. We're going to make you pay in compute for login. And the more you're going to try, the more expensive it's going to be for you. Just compare that to toll road. You have to pay the toll. If you're going to a time that is high traffic, your toll is going to be more expensive. If you have a special vehicle, like you want to log into an account that has administrative privilege, it's more expensive as well. That's what we have for today. Do you guys have any question for us?
Did you implement, so you had the chart for JavaScript times. I didn't see if there was a line for like a straight C implementation, just to see what on the same processor, what an attacker could do if they wrote something reasonably optimized. Do you know how fast you could go on a machine versus what JavaScript does?
You could go significantly faster with a straight C implementation.
And a GPU is in the hundreds of millions per second. So if you could punt it down there, yeah.
So you can also parallelize that. If we ask you 12-bit, you just put one core for one GPU core for each possible solution, and you can parallelize that. But you still have to do the work. You're going to spend your compute. You're going to be computing very fast, but you're going to have to do it. So if you're an opportunistic attacker trying to scan the whole internet, just having a simple machine or a botnet of 50 machines doing that, that's not going to work anymore. You need to have a machine with GPU, you need to develop special code, so your return of investment is really poor because your compute cost is very high.
You talked about being able to move to different algorithms, which I guess is fairly straightforward if you were pushing out JavaScript to the client side that does that. Have you thought about how this would apply in either mobile applications or authenticated APIs where you don't have the ability to push that out the same way?
Well, I think part of the API was that if we're not pushing the code directly, in a lot of cases we're pushing the question to the client, saying, I want you to compute for me with this nonce, 12 bits, partial collision. And then, at least in the JavaScript implementation, we had some arrays that would control which algorithms and in which order to apply, in the hopes that people trying to do optimized versions of this would be forced to either analyze it or write custom code and try to link together stuff that eventually would be not fruitful for them.
So if you have an implementation that is not using JavaScript, you're going to lose some flexibility. Our goal long term is to give you JavaScript code that you will have to execute. We won't tell you what's in there. It will be randomly generated, and you will have to run it. There's always a possibility to do analysis and to find shortcut, but consider it like a white box crypto. Here's some code that in JavaScript that will do a proof of work for you. I'm not telling you what it is. You have to analyze it if you want to find a shortcut. It's a hard problem there. And that code is going to change every time you're asking for a proof of work.
I think it's first section. The form-based
three-stage HTML implementation with the JavaScript seems pretty straightforward. Just wondering what the thoughts were for implementation of another protocol such as IMAP or SSH. What would it take to really add that security to my system?
That would be relatively straightforward. In terms of implementation, that's easy to do. It's not going to be a lot of work. The problem with something like SSH is that now you're going to have a custom SSH server and you need to custom SSH client. So if that kind of technique is not widely adopted, you're going to lose interoperability. That's why we started with a web-based POC, because that's easy to implement. You have interoperability. You have no user friction there. It's very little work there. You can write that in one day. You can look at the sample code that we have, push that onto your server. And because the server controls the client there, you don't have deployment problem. You don't have interoperability problem. You just have a requirement to run JavaScript.
So with your current implementation or current description, it sounds like what you send to the client is some nonce and some target collision amount. And so the only way to prevent a basic attack, like the client gets some nonce, some collision amount, and the client says, oh, I'm just going to ignore this nonce, I'm going to generate my own. And I'm going to ignore the collision amount, I'm going to generate my own, and I'm going to send my own simpler challenge back. The only way that you guys would know that that's not a valid one is if you stored the challenge that you sent in the database. So have you thought of, and so then you have this attack where you're inserting all this stuff into the database. Have you thought of using some sort of crypto that has like a timestamp and a HMAC, so you can verify without persisting any state that what you sent them or what you got back from them is actually what you sent them.
Already answered the right question.
We do use a session to store that information. So we don't really use a database for that. We could use a database for that. So with your HTTP session, you'll get a cookie, and with that cookie, we have a session on the server, and we're storing the problem. And you have to answer that problem.
And you're using memory on the server. That was my point.
Yes,
yeah. The memory-less implementation.
Yes.
Yeah, and I think the other point is you'll see at one point you come back with an answer, and we go ahead and just take your answer and then use the value stored in the session to compute it, and just ignore your other stuff that you gave us, assuming that they were going to lie to us anyway.
You don't have to send back the nonce. That would be if we start considering the nonce send back, we will have to think about a crypto protocol where we could verify that you're not sending something twice, that you're not generating the work on your side. That's probably a harder problem to solve. Any other questions?
Okay, thank you.
Thank you very much. Feel free to contact us, and we have everything on GitHub. So it's github.com/JaegerIndustries/passwords14. There's a PDF of the presentation. There's a PHP code that includes the JavaScript. There's a working POC. You can play with it. It shows you all the parameters. Just don't use a sample code as a secure implementation. It's not. Thank you so much.